The search for extra dimensions is one of the most exciting frontiers in modern physics. These hidden spaces, predicted by theories like string theory and Brane cosmology, could explain why gravity is so weak compared to other forces. But how would we ever detect something we cannot see? This video is a tour of 20 different experiments that could provide the first evidence. After watching, you will know exactly how scientists are hunting for extra dimensions using everything from particle colliders and gravitational wave observatories to tabletop devices and astrophysical surveys. So far, none have succeeded, but the race is on. Could microscopic black holes appear inside the Large Hadron Collider? Do gravitational waves carry whispers of extra dimensions? What would it mean for our understanding of reality if we discovered a hidden dimension? Missing energy at the Large Hadron Collider could be the signature of extra dimensions. When particles smash together inside the collider, most of the energy stays within the detector. But if extra dimensions exist, some of that energy might slip away into the hidden space. The carriers of this energy would be gravitons, the hypothetical particles that transmit the force of gravity. In ordinary physics, gravitons interact very weakly. But in theories with extra dimensions, gravitons could be produced more frequently in high-energy collisions. Once created, they would immediately escape into the extra dimensions, taking energy with them and never interacting with the detector again. That lost energy leaves a clear fingerprint. Physicists call it missing transverse energy. In a typical collision, the total momentum of all the particles measured in the detector should add up to zero, since the initial particles were moving head-on. If one side of the detector sees less energy than expected, something invisible carried it away. The signature is especially clean when a single energetic jet of particles or a single high-energy photon is produced on the opposite side. The collision looks unbalanced, as if something punched through without leaving a trace. The ATLAS and CMS detectors, two massive experiments at the Large Hadron Collider, carefully measure this imbalance. They scan billions of collisions, looking for events where a single jet or photon is accompanied by a large amount of missing energy. These searches have already placed strong limits on the size of extra dimensions. If extra dimensions are large enough, gravitons would be produced more often, and the missing energy signal would become clear. So far, no such signal has been seen, which means that if extra dimensions exist, they must be smaller than about 1/10 of a millimeter. That may sound tiny, but in the world of particle physics, it is actually enormous. Most fundamental forces operate at scales far smaller than a billionth of a meter. A dimension 1/10 of a millimeter wide would be a giant compared to the subatomic realm. The absence of a signal also rules out the simplest models of large extra dimensions, but it does not rule out all possibilities. The LHC continues to push the search to higher energies and more subtle signals. Missing energy is an indirect probe. It only tells us that something invisible is carrying away momentum. But the same collisions could produce something far more dramatic. If extra dimensions exist and gravity becomes strong at the TV scale, then the LHC might create microscopic black holes. These black holes would be tiny, weighing about as much as a heavy particle, and they would evaporate almost instantly in a burst of radiation. Detecting that burst would be a direct sign of extra dimensions. So while the quiet missing energy search continues, scientists are also watching for the most violent possible signature. The transition from missing energy to black holes is only a step away. When that step is taken, the LHC could create microscopic black holes. This possibility depends on something called the fundamental Planck scale. In our everyday world, gravity is incredibly weak. but in theories with extra dimensions, gravity could become much stronger at small distances. If that fundamental scale is low enough, around a few trillion electron volts, then the energy concentrated in a single collision at the LHC might be enough to form a black hole. Not the kind that swallows stars, but something far smaller. A micro-black hole would weigh about as much as a heavy atomic nucleus, but be compressed into a region far smaller than a proton. Its existence would be fleeting. According to Stephen Hawking's theoretical work, black holes emit radiation and slowly lose mass. For a micro-black hole, that process would happen almost instantly, in a tiny fraction of a second. The black hole would decay into a burst of particles, radiating a spray of jets, electrons, muons, and photons all at once. That signature is unmistakable. In a normal collision, particles tend to come out in a focused stream with balanced energy. A decaying micro-black hole would produce a spherical explosion of many high-energy particles flying in all directions, a so-called high multiplicity event. Detecting even a single such event would be definitive proof that extra dimensions exist. It would also tell scientists that the fundamental Planck scale is exactly where the black hole formed. But so far, after years of searching, no micro-black holes have appeared. That missing signal has allowed researchers to place lower limits on the Planck scale. They can say that if extra dimensions exist, the fundamental scale must be above roughly 5 trillion electron volts. That is a higher energy than the LHC can currently reach, which explains why no black holes have been seen. The search continues with each new run of the collider, pushing the boundary further. Even without finding black holes, these null results are valuable. They refine the models and guide theorists toward more realistic versions of extra-dimensional physics. But a negative result in one type of experiment does not close the book on extra dimensions. They might reveal themselves in a completely different way through the ripples they send across the cosmos. Gravitational waves, the distortions in spacetime caused by massive cosmic events, could carry subtle traces of hidden dimensions. That leads into a different kind of search, one that looks not at particle collisions but at the echoes of colliding black holes and neutron stars. When two black holes spiral together, they send ripples through spacetime. These ripples are gravitational waves, and they travel across the universe at the speed of light. When they reach Earth, observatories like LIGO and Virgo detect them as tiny, fleeting changes in the length of their arms. The shape of the wave, its frequency, and how it fades away all carry information about the collision that created it. If extra dimensions exist, they could leave a subtle fingerprint on that waveform. One possible modification is a change in the ringdown phase. After two black holes merge, the new, larger black hole settles into a stable shape. It vibrates like a struck bell, emitting gravitational waves at specific frequencies. Those frequencies depend only on the mass and spin of the black hole, at least in ordinary general relativity. But if extra dimensions exist, the black hole might vibrate differently. The ringdown could contain additional tones, higher or lower than expected, or the original frequencies might be shifted. Researchers at LIGO and Virgo compare every observed ringdown to theoretical predictions. So far, the matches are perfect, but future events or more sensitive detectors could reveal a discrepancy. Another signature could be high-frequency echoes. Some models predict that extra dimensions create a sort of boundary layer near the black hole. When gravitational waves pass through that boundary, they can reflect back, producing a series of faint echoes after the main signal. These echoes would arrive milliseconds to seconds later, depending on the size of the extra dimensions. LIGO has searched for such echoes in data from dozens of black hole mergers. None have been found yet, but the search continues with every new detection. Extra dimensions could also cause a loss of energy that mimics dark radiation. In general relativity, a black hole merger releases a specific amount of energy as gravitational waves. The amplitude of the waves tells us how much energy was carried away. If some of that energy leaks into extra dimensions, the waves we see would be weaker than expected. The missing energy would look like a form of dark radiation, an invisible component that does not interact with ordinary matter. Cosmologists have already placed tight limits on dark radiation from the early universe, so this is a narrow window, but a single mismatched gravitational wave event could point directly to extra dimensions. The beauty of gravitational wave tests is that they are model-independent. You do not need to assume a specific theory of extra dimensions. You simply look for deviations from the predictions of ordinary general relativity. If you see something unexpected, you know new physics is at work. The challenge, however, is that many kinds of new physics could produce similar signals. Modified gravity theories, alternative theories of black holes, and even exotic compact objects could mimic the same echoes or altered ringdowns. Separating extra-dimensional effects from these alternatives will require many events and precise measurements. Future observatories will sharpen this search. The Laser Interferometer Space Antenna, or LISA, will watch for lower-frequency gravitational waves from supermassive black hole mergers. Those events are billions of times more massive than the ones LIGO sees, and they could reveal extra-dimensional effects at different scales. Also, new ground-based detectors like the Einstein telescope will be far more sensitive, able to pick up fainter echoes and smaller deviations. But even if gravitational waves remain silent, extra dimensions might still be hiding in plain sight, right here on Earth. The next step is to test gravity at the smallest possible distances, using tabletop experiments that measure the force between tiny masses. Those experiments could detect the gravitational fingerprint of a hidden dimension directly. The Casimir force is a strange quantum effect that becomes measurable at tiny distances. When two conducting plates are placed extremely close together, less than 1,000th of a millimeter apart, the vacuum itself pushes them toward each other. This happens because only certain quantum fluctuations of the electromagnetic field can exist in the narrow gap between the plates. The result is a tiny but measurable attraction. The strength of this force depends very precisely on the distance between the plates, and it follows a specific formula predicted by quantum electrodynamics. If extra dimensions exist, they would alter that formula. In theories with large extra dimensions, gravity and other forces could behave differently at sub-millimeter scales. The Casimir force, being an electromagnetic effect, would not be directly changed by gravity, but the extra dimensions would modify the overall geometry of spacetime. That modification would cause the Casimir force to deviate from the standard prediction, especially at distances smaller than the size of the extra dimensions. The deviation could be a shift in the force's strength or a change in how it falls off with distance. Detecting such a shift requires extraordinary precision. The force between two plates just a few hundred atoms apart is incredibly weak, about a billionth of a Newton. That is roughly the weight of a single red blood cell. Measuring it accurately demands exquisitely sensitive instruments. One common approach uses an atomic force microscope. A tiny sphere is attached to a cantilever, and the sphere is brought very close to a flat plate. As the Casimir force pulls the sphere toward the plate, the cantilever bends ever so slightly. A laser beam reflected off the cantilever measures that bending to within a few billionths of a meter. By moving the sphere to different distances and recording the force, researchers can map out the Casimir interaction with great accuracy. Another technique uses a torsional pendulum. A small metal plate is suspended by a thin fiber, and another plate is positioned nearby. The Casimir force twists the pendulum, and the amount of twist is measured with extreme precision. Both methods have been used to test the Casimir force at distances from 10 micrometers down to about 100 nanometers. So far, the measurements match the predictions of quantum electrodynamics perfectly. That means any extra dimensions must be smaller than about 10 micrometers. If they were larger, the deviation would have been seen. These experiments have already ruled out extra dimensions larger than roughly 1/100th of a millimeter. That is 1,000 times smaller than the width of a human hair, but the search does not stop there. Researchers are now pushing to even smaller distances, using specialized techniques to probe gaps of just a few nanometers. At those scales, the Casimir force becomes stronger and any extra-dimensional effect would be more pronounced. However, other complications arise. Surface roughness, electrostatic forces, and contamination can mask the signal. Scientists must carefully control every variable, often running experiments in ultra-high vacuum and at cryogenic temperatures to reduce noise. The sensitivity required is extraordinary, but the payoff is huge. A single hint of a deviation could be the first direct evidence of extra dimensions. These tabletop experiments are complementary to the particle collider searches. They probe different size scales and different types of extra dimensions. While the LHC looks for missing energy and black holes at energies above 1 trillion electron volts, the Casimir experiments examine the behavior of forces at distances far smaller than a millimeter. Together, they cover a wide range of possibilities, but even the most precise Casimir measurements have not yet reached the ultimate limit. To go deeper, physicists have turned to an even more fundamental test, measuring gravity itself at the smallest possible distances. The gravitational force is far weaker than the Casimir force, making it even harder to measure. But if extra dimensions exist, gravity could become strong at sub-millimeter scales. That would create a detectable anomaly in how gravity behaves between two tiny masses. The most sensitive tool for this task is the torsion balance, an instrument that has been used for centuries to measure the gravitational constant and test the inverse square law. The next experiment in our journey uses this classic device to search for the faintest gravitational signals ever measured. Gravity has been tested down to the smallest distances ever measured using a device called the torsion balance. The most famous of these experiments is the Eöt-Wash project, named after the Hungarian physicist Laurent Eöt-Wash, who pioneered precision torsion balance work over a century ago. In this modern version, researchers suspend a thin metal disc or a ring from a delicate fiber, then bring a rotating attractor mass very close to it. The attractor is shaped with specific patterns, often a set of holes or a series of alternating sectors, so that as it rotates, the gravitational pull on the suspended mass changes in a periodic way. If gravity follows the inverse square law, the force should fall off exactly proportional to 1 over the distance squared. But if extra dimensions exist, the force could deviate at short distances because gravity might spread into those hidden directions. That deviation would show up as a measurable torque on the torsion pendulum, a twisting force that would cause the suspended mass to oscillate in a pattern not predicted by known physics. The experiment measures these tiny twists with extraordinary precision, using laser beams and mirrors to track movements of a few billionths of a degree. Over the years, the Eöt-Wash group has pushed the search down to distances of about 50 micrometers, roughly half the thickness of a human hair. They have found no deviation from the inverse square law, which means any extra dimensions must be smaller than about 40 micrometers. That limit is among the most stringent for large flat extra dimensions, the kind predicted by some Brane world models. The torsion balance is essentially a direct probe of how gravity behaves at the smallest accessible scales, measuring the force between two macroscopic objects separated by a hairbreadth gap. It is a quiet experiment, not as flashy as the LHC, but it reaches into a regime where gravity itself might reveal its hidden structure. The fact that no anomaly has been seen means extra dimensions, if they exist, must be even smaller than 40 micrometers, or else gravity behaves differently at still tinier distances. And that raises a new question. If we cannot detect any deviation down to the micrometer scale, what about the gravitational constant itself? Measuring the strength of gravity, Newton's constant, has been notoriously difficult. Different experiments give slightly different values, a disagreement that has persisted for decades. Some scientists wonder if this persistent puzzle could be a subtle sign of extra dimensions, a tiny inconsistency in how gravity appears to us from inside our three-dimensional brain. That mystery connects directly to the next experiment, which tries to resolve the tension by making the most precise measurements of g ever attempted. The gravitational constant refuses to be pinned down. For centuries, physicists have measured the strength of gravity, trying to determine Newton's constant with ever greater precision. Yet the results stubbornly disagree. Different experiments using different techniques produce values that differ by more than their stated uncertainties. This persistent inconsistency is one of the quiet puzzles at the heart of modern physics. Some researchers believe it could be a clue pointing toward extra dimensions. In ordinary three-dimensional space, gravity follows the inverse square law, and its strength, Newton's constant, is a universal number. But if extra dimensions exist, the effective strength of gravity could change with distance. At very small separations, gravity would feel the extra space and become stronger or weaker depending on the geometry. This means the value you measure depends on the scale of your experiment. A torsion balance testing gravity at the micrometer scale might see a different constant than a pendulum experiment that operates at centimeter distances. The conflicting measurements we see today might not be errors at all, but a real physical effect, a subtle fingerprint of hidden dimensions. To test this idea, scientists are building the most precise gravity experiments ever conceived. One approach uses cold atoms. Clouds of atoms are laser-cooled to near absolute zero, then launched upward in a vacuum chamber. As they rise and fall, they are split into two paths by laser pulses, like the arms of an interferometer. The gravitational pull on each path is slightly different, and when the atoms recombine, the interference pattern reveals the strength of gravity with extraordinary sensitivity. These atom interferometers can measure Newton's constant at the scale of a few centimeters, and they are now being pushed to even smaller distances. Another technique uses advanced optical interferometers where laser light bounces between freely falling mirrors inside a vacuum. By tracking the motion of these test masses with nanometer precision, researchers can measure how gravity changes as the masses are moved closer together. The goal is to detect any deviation from the constant value, any variation that would signal extra dimensions affecting gravity at a particular length scale. So far, no such variation has been seen, but the precision improves each year. The window where extra dimensions could hide grows smaller, yet gravity is not the only way to search. Particle colliders offer a completely different window, one where energy, not distance, is the probe. In high-energy collisions, extra dimensions could reveal themselves through the production of new particles or through subtle shifts in the behavior of known ones. The next set of experiments examines how the universe's most powerful accelerators are hunting for dimensions invisible to the eye. Neutrinos are the ghostliest particles we know, and they might carry the faintest whisper of extra dimensions. These particles barely interact with matter, streaming through entire planets without a trace. Yet they do something strange. They change identity as they travel. A neutrino born as an electron type can later appear as a muon type or a tau type. This process is called oscillation, and it depends on tiny differences in mass between the three known flavors. But if extra dimensions exist, an entirely new possibility opens up. Neutrinos could oscillate into a sterile flavor, one that does not interact with ordinary matter at all. In models with extra dimensions, sterile neutrinos are not confined to our three-dimensional brane. They can propagate through the bulk of the higher dimensional space, moving freely in directions we cannot see. That ability changes the oscillation probabilities we observe. The active flavors would appear to oscillate at different rates because some of the neutrino wave function leaks into the hidden dimensions. Experiments around the world are hunting for exactly this kind of anomaly. The mini booster neutrino experiment at Fermilab shoots a beam of muon neutrinos at a detector less than a kilometer away. For years, it has seen an excess of electron neutrinos, more than standard three-flavor oscillations predict. This anomaly has sparked intense debate. Some physicists believe it could be a sign of a sterile neutrino, and that sterile neutrino could be the direct imprint of an extra dimension. Other experiments, like the Tokai to Kamioka experiment in Japan and the new MI off-axis experiment in the United States, look at neutrinos that travel hundreds of kilometers. They compare the rate of muon neutrinos disappearing and electron neutrinos appearing over those long distances. So far, their results have not shown a clear deviation from the standard three-flavor picture. But the tension remains, the short baseline anomaly persists, and extra dimensions offer a natural explanation. Future detectors will push the search much further. The Deep Underground Neutrino experiment, currently under construction in the United States, will send a neutrino beam from Fermilab to a massive detector in South Dakota, a distance of more than 1,000 kilometers. Its extraordinary sensitivity will allow physicists to measure oscillation probabilities with unprecedented precision. If extra dimensions are causing sterile neutrino mixing, Dune will see subtle distortions in the expected pattern. The shape of the oscillation curve, the height of its peaks, and the spacing between them could all be shifted. Even a tiny deviation could point the way. The fact that sterile neutrino hints have not gone away despite decades of searching makes the extra-dimensional explanation all the more compelling. And if neutrinos can slip into unseen dimensions, perhaps other cosmic messengers can too. At the highest energies ever observed, particles called cosmic rays strike Earth's atmosphere with energies millions of times greater than anything produced in human-made colliders. Those extreme energies could reveal extra-dimensional effects in ways that neutrino experiments cannot reach. Cosmic rays carry more energy than any collider can ever achieve. The most powerful ones strike Earth's atmosphere with energies 100 million times greater than the collisions inside the Large Hadron Collider. When such a particle hits the air, it triggers a cascade of secondary particles, a shower that spreads across kilometers and reaches the ground. The Pierre Auger Observatory, a vast array of detectors in Argentina, captures these air showers and reconstructs what happened at the very top of the atmosphere. It measures the number of particles, their types, and how the shower develops. If extra dimensions exist, some of those extreme energy cosmic rays could produce particles that only exist in higher dimensional spacetime, known as Kaluza-Klein particles. In theories with extra dimensions, every known particle has heavier partners that can move into the hidden space. The simplest version involves Kaluza-Klein gravitons. A cosmic ray proton or nucleus slamming into an air molecule at near light speed could create a graviton that then escapes into the extra dimension, taking energy away. But that graviton would also interact gravitationally with ordinary matter, producing a secondary burst of particles that looks different from a standard shower. The signature is subtle. In a normal air shower, the number of muons and the depth where the shower reaches its maximum size follow a predictable pattern. A Kaluza-Klein process would change that balance. The shower might contain an excess of muons because graviton decays produce pions that decay into muons. Or the electromagnetic component might be suppressed because energy is siphoned off into invisible particles. Researchers at the Pierre Auger Observatory compare every observed shower to detailed computer simulations. They look for anomalies in the muon content, the lateral spread, and the fluctuation from event to event. So far, after analyzing thousands of the highest energy showers, they see no statistically significant deviation. That places limits on the cross-section for producing Kaluza-Klein particles, which in turn constrains the size and number of extra dimensions. The search is far from over. The observatory continues to collect data, and a planned upgrade will improve the sensitivity to muon measurements, allowing scientists to detect even smaller deviations. But the null results have a deeper implication. Even if extra dimensions are too small to be seen at the LHC and too subtle for gravitational wave detectors, they might still leave a faint trace in the rarest, most energetic events in the universe. And that line of reasoning leads to a question that connects extra dimensions to one of the biggest mysteries in cosmology. What is dark matter? The particle that fills the cosmos, invisible yet gravitationally influential, could be a Kaluza-Klein particle itself, a stable relic from the early universe that moves through extra dimensions. The answer to that mystery might be hiding in plain sight as a particle that is perfectly stable because it lives in extra dimensions. Consider the lightest Kaluza-Klein mode of a familiar particle. In many models, the lightest one is a partner of the photon. It does not decay because there is nothing lighter for it to turn into, and that stability makes it an ideal candidate for dark matter. This particle would interact very weakly with ordinary matter, just enough to be detectable but not enough to have been found already. Experiments like LZ, Xenon-NT, and Panda-X are built to catch that faint interaction. They use enormous tanks of liquid xenon, cooled to very low temperatures and shielded deep underground from cosmic rays. When a Kaluza-Klein dark matter particle passes through the detector, it could bump into a xenon nucleus, causing a tiny recoil that releases a flash of light and a small electric charge. The detectors are exquisitely sensitive, capable of seeing a single interaction in a ton of xenon over months of running. So far, none of these experiments have observed a convincing signal. But they continue to get more sensitive with each upgrade, pushing the limits on how strongly dark matter can interact. The null results rule out certain masses for Kaluza-Klein dark matter, especially in the range around 100 times the mass of a proton. Yet the search is far from over. Another way to find these particles is to look for the annihilation products where dark matter is densest. The galactic center is full of dark matter, and if Kaluza-Klein particles meet there, they could annihilate into ordinary particles, including gamma rays. The Fermi Large Area Telescope has been scanning the sky in gamma rays for over a decade. It sees a bright glow from the center of our galaxy, but much of that comes from known sources like pulsars and supernova remnants. After subtracting those, a faint residual signal remains, one that could come from dark matter annihilation. However, the interpretation is controversial. Some analyses suggest the excess matches the predicted signature of a 150 giga-electron-volt particle, consistent with a Kaluza-Klein dark matter candidate. Others argue that unresolved point sources like millisecond pulsars could produce the same signal. The debate continues. If future gamma-ray telescopes like the Cherenkov Telescope Array can confirm that the excess has exactly the right spectrum and spatial shape, it would be a smoking gun. And because the only way to have a stable Kaluza-Klein photon is if extra dimensions exist, that detection would be direct evidence of hidden space. That is an extraordinary possibility, and it connects the largest mystery in cosmology to the most esoteric idea in particle physics. But even if dark matter turns out to be something else, the stage is set for another dramatic test. The same extra dimensions that could hold dark matter could also warp spacetime in a way that leaves a distinct mark on gravitational waves. In Brane world scenarios, our entire universe is a three-dimensional sheet floating in a higher dimensional bulk. When black holes or neutron stars collide on our Brane, they could send ripples not only along the brane but also into the bulk. Those bulk ripples would carry away energy, making the gravitational waves we observe slightly weaker and slower than expected. And unlike the generic extra-dimensional effects described earlier, brane world models predict a specific pattern in the waveform, a telltale distortion that no other theory mimics. Brane collisions in the early universe would leave behind a distinct echo. In brane world models, our three-dimensional universe is a sheet floating in a higher dimensional space called the bulk. Other branes could exist two separate sheets that drift through the bulk. When two such branes collide, the impact releases an enormous amount of energy, creating ripples in spacetime that travel outward as gravitational waves. These waves would be different from the ones produced by black hole mergers. They would have a unique frequency profile, often peaking in a range that LIGO and Virgo can detect. The collision event itself would be brief, but the resulting gravitational wave signal could be a sudden burst or a continuous hum depending on how the branes interact. Some models predict that many such collisions happened in the first moments after the Big Bang, generating a random background of gravitational waves called a stochastic background. This background would be a faint hiss across all frequencies, like the static from an old radio. LIGO and Virgo have been searching for exactly that kind of stochastic signal. They look for correlated noise between their two detectors, a sign that a real gravitational wave passed through both sites at the same time. So far, no such correlation has been found. The upper limits from those searches place strong constraints on how often brane collisions could have occurred and how energetic they were. If the stochastic background were any stronger, it would have been seen. That means brane collisions, if they happened, must have been rare or produced weaker waves than some models predicted, but the search is far from over. The detectors are becoming more sensitive with each upgrade, and they are also listening for individual burst events that might stand out from the background. A single loud brane collision could produce a ringdown pattern similar to a black hole merger, but with a different shape. Researchers comb through the data looking for any anomaly that matches the predicted waveform. None have been found yet, but the possibility keeps the hunt alive. Future observatories will open a whole new window. The Laser Interferometer Space Antenna, or LISA, will be sensitive to much lower frequencies, from a few tenths of a millihertz up to about a tenth of a hertz. In that range, brane collisions from the early universe would leave a clearer fingerprint. LISA could see a continuous hum that persists across years, a steady signal that no other source could mimic. Its launch is planned for the next decade, and it promises to probe energies and timescales far beyond anything reachable from Earth. If extra dimensions are responsible for that hum, the discovery would reshape our understanding of cosmic history. But even if LISA sees nothing, the constraints will tighten further, refining the models and guiding theorists toward more realistic versions of brane cosmology. The same reasoning applies to another class of experiments, precision tests of fundamental symmetries. Extra dimensions could subtly break symmetries we take for granted, leaving tiny cracks in the laws of physics that experiments on Earth might detect. The most fundamental symmetry of physics is Lorentz invariance. It is the principle that the laws of nature are the same no matter how fast you are moving or in which direction you are pointing. This symmetry has been tested more thoroughly than almost any other idea in science. Every experiment ever performed, from the spin of an electron to the flight of a rocket, has assumed it holds true. Yet extra dimensions could break this symmetry in a subtle but detectable way. The reason is geometric. Our universe is a three-dimensional brane embedded in a higher dimensional bulk. The bulk might have its own properties, and the way our brane moves through it could pick out a preferred direction or a preferred speed. That would mean the laws of physics are not exactly the same in all frames, breaking Lorentz invariance. The break would be tiny but measurable with the right tools, Atomic clocks are among the most sensitive probes of this kind of break. These clocks keep time by counting the oscillations of atoms, typically cesium or rubidium, as they transition between energy levels. The frequency of that transition is incredibly stable, better than 1 part in a million billion. If Lorentz invariants were broken, the frequency might change depending on the orientation of the clock relative to some preferred direction in space. To test this, researchers compare 2 atomic clocks that point in different directions, often using a rotating table to spin the entire apparatus. As the clocks rotate, any variation in their tick rates would reveal a violation. Experiments at institutions like the National Institute of Standards and Technology have placed limits on such variations at the level of 1 part in 10 to the 18th. That is like measuring the distance from Earth to the Moon to within the width of a human hair. No violation has been found, which means any extra-dimensional effect on Lorentz symmetry must be extraordinarily weak. Another type of test uses cavity resonators. These are precisely machined chambers, often made of sapphire or quartz, that trap electromagnetic waves at specific frequencies. The speed of light inside the cavity depends on its shape and orientation. If Lorentz invariance holds, that speed should be the same no matter how the cavity is turned. But a preferred direction from extra dimensions could cause the speed to vary slightly, shifting the resonance frequency. Modern experiments compare 2 orthogonal cavities, one aligned with a possible preferred axis and one perpendicular, and look for any difference as Earth rotates. The most famous such test is a modern version of the Michelson-Morley experiment, which originally showed that the speed of light is constant. Today's versions use lasers stabilized to these cavities and achieve sensitivities that would detect a fractional change in the speed of light as small as 10 to the minus 17. Again, no deviation has been seen. Astrophysical observations offer a completely different window. Light from distant galaxies and gamma-ray bursts travels for billions of years across the universe. If Lorentz invariance is broken, different wavelengths of light might travel at slightly different speeds, a phenomenon called dispersion. Alternatively, polarized light might rotate as it travels, an effect called birefringence. Telescopes like the Fermi Gamma-Ray Space Telescope have watched high-energy photons from distant explosions and measured their arrival times with exquisite precision. They see no dispersion, meaning the speed of light is constant to within a part in a million billion across a huge range of energies. Polarization data from sources like quasars also show no birefringence. These astronomical limits are so tight that they rule out many extra-dimensional models that would predict noticeable Lorentz violation. But the search is not confined to quiet laboratories and distant skies. High-energy collider experiments also probe Lorentz invariance. Inside the Large Hadron Collider, particles are accelerated to speeds extremely close to the speed of light, and their interactions are studied in detail. If Lorentz symmetry were even slightly broken, it would alter the cross-sections of certain collisions, the rates at which particles are produced, and the angular distributions of the debris. The ATLAS and CMS detectors have searched for signatures like a directional dependence in the production of top quarks or W bosons. They have found nothing. Together, all these tests have pushed the possible size of Lorentz violation to levels that are incredibly low, billions of times smaller than the effects predicted by some simple extra-dimensional models. Yet the door remains open. The next generation of atomic clocks using optical transitions in ions or neutral atoms will improve sensitivity by another factor of 100. Space-based missions like the proposed ST-Quest experiment would place clocks on satellites free from Earth rotation and gravity, allowing even cleaner tests. If a violation is ever found, it would not only confirm extra dimensions but also reveal a deep property of the fabric of spacetime, that the universe has a subtle directionality hidden beneath the smooth laws we observe. Until then, each null result narrows the possibilities, guiding physicists toward a more precise understanding of how extra dimensions might actually be arranged. And that understanding must also account for another, even stranger possibility, that extra dimensions are not large and flat, but instead curled up into shapes so tiny that they can only be seen with the most powerful microscopes in existence, probes that look at the behavior of particles at the highest possible energies. The Large Hadron Collider could create heavy graviton particles from curled-up extra dimensions. In the Randall-Sundrum model, an extra dimension is not flat but warped, like a funnel that squeezes spacetime into a small region. This warping means that gravity, normally weak, becomes strong at energies the LHC can reach. The result is a set of particles called Kaluza-Klein gravitons, with the lightest one possibly as massive as a few trillion electron volts. When a graviton is produced in a proton-proton collision, it decays almost instantly into two jets, two photons, or two leptons, such as electrons or muons. Those decays would show up as a narrow peak in the mass spectrum of those pairs, a bump rising above the smooth background of ordinary standard model processes. The key to telling a graviton apart from other possible new particles is its spin. A graviton has spin 2, which means it carries 2 units of angular momentum. That spin gives its decay products a very specific angular distribution. For a spin 2 particle, the angle between the two outgoing jets or photons follows a pattern that is different from the pattern produced by a spin 1 particle like a Z prime, or a spin 0 particle like a Higgs boson. By measuring how often the particles emerge at different angles, physicists can determine the spin of the resonance. In addition, a graviton interferes with the standard model background in a distinct way. For example, in the diphoton channel, the graviton and the background from quark annihilation produce a subtle shift in the shape of the mass peak. That interference pattern provides another fingerprint. Both ATLAS and CMS have searched for such peaks in the digit, diphoton, and dilepton channels using data from the LHC runs. They have looked for resonances with masses from a few 100 billion electron volts up to several trillion electron volts. No convincing signal has been found. The current exclusion limits place the lightest graviton mass above roughly 2 trillion electron volts, depending on the coupling strength in the model. If the coupling is very weak, the graviton could be lighter but still not produced often enough to have been seen. These null results are valuable because they rule out the simplest versions of the Randall-Sundrum model with a single warped dimension. But the search continues with each new LHC collision, and future runs at higher energies could push the limits further. Even if no graviton is found at the LHC, the same warped dimensions could leave a deeper imprint on the universe. Neutron stars, the densest objects known, might feel the effects. When two neutron stars collide, their immense gravity could excite a graviton resonance, altering the gravitational wave signal. That connection between collider physics and multi-messenger astronomy is the next frontier. One specific neutron star merger changed everything. On August 17, 2017, the LIGO and Virgo detectors caught the gravitational waves from two dense stellar remnants spiraling into each other. Just 1.7 seconds later, the Fermi Gamma Ray Space Telescope detected a burst of gamma rays from the same location. Hours after that, telescopes around the world turned to the distant galaxy and saw the glow of a kilonova, the explosion of heavy elements forged in that merger. The event was called GW 170,817. It was the first time a gravitational wave signal had a confirmed electromagnetic counterpart, and that combination turned it into a perfect test for extra dimensions. In theories with extra dimensions, gravity can leak into the bulk. That leakage would carry away energy that would normally stay in the gravitational wave signal we see. If that happened, the neutron stars would lose orbital energy faster than expected, spiraling together more quickly. The waveform of the gravitational waves would show a different shape, a faster in-spiral that would not match the predictions of general relativity. Additionally, if gravity traveled at a different speed through the extra dimensions, the time delay between the gravitational wave peak and the gamma-ray burst could be shifted. Because the two signals arrived within less than 2 seconds after traveling over 100 million light-years, scientists knew that gravity and light move at essentially the same speed. That ruled out any extra-dimensional model that would cause a significant difference in their velocities, but the strongest constraint came from the waveform itself. The shape of the GW 170,817 signal matched the predictions of ordinary four-dimensional general relativity with astonishing precision. There was no sign of extra energy loss. That meant any extra dimensions larger than about a few micrometers could not exist in large numbers. In fact, the observation placed a firm limit. If there are more than 2 large extra dimensions, the signal would have been measurably different. The data ruled out scenarios with 3 or more large extra dimensions, and it also narrowed the allowed size for a single large extra dimension to less than about 1 micrometer. The result was one of the most powerful astrophysical constraints on extra-dimensional theories ever obtained. The event also tested the nature of the bulk itself. Some models predict that gravitational waves could excite vibrations in the extra dimensions or produce echoes. No such echoes were seen in the ringdown of the merger. The absence of these anomalies tightened the bounds on warped extra-dimension scenarios as well. Even the color and brightness of the kilonova placed limits. If extra dimensions had altered the gravitational binding energy of the neutron stars before the merger, the amount of ejected material and the heavy element synthesis would have changed. The observed kilonova matched the standard picture perfectly. All these independent checks converged on the same conclusion. If extra dimensions exist, they must be very small, or they must be structured in a way that barely affects the merger of neutron stars. The silence from that single event is deafening, but it is also illuminating. It tells physicists exactly where not to look next. The constraints from GW 170,817 are now built into every new model of large extra dimensions. Meanwhile, the search continues in a completely different direction. Some of the rarest particle decays ever studied, processes that happen once in trillions of events, could reveal the faintest whisper of hidden space. Even the rarest particle decays can hold the deepest secrets. Inside the Large Hadron Collider and other accelerators, particles called B-mesons are produced by the billions. These particles are heavy, unstable, and they decay in many different ways. Physicists study every possible decay channel, looking for anything that does not match the standard model predictions. One of the most intriguing searches focuses on a specific decay, a B-meson transforming into a K-meson plus nothing visible at all. The nothing is missing energy. In the standard model, such a decay can happen through the weak interaction, producing a pair of neutrinos that escape detection. That process is incredibly rare. But in theories with extra dimensions, it could be much more common. A B-meson could emit a Kaluza-Klein graviton or a particle that propagates into the bulk, carrying away energy without leaving a trace. The experimental signature is the same as the standard model neutrino process, a K-meson with a well-defined energy and momentum, and nothing else in the detector. The difference is the rate. If extra dimensions exist, the rate of B to K plus missing energy would be measurably higher than the standard model predicts. Experiments like LHCb at the LHC and Bell Roman 2 in Japan are designed to catch exactly this kind of anomaly. They track every particle produced in the collision, reconstruct the full event, and look for the telltale imbalance. LHCb uses a forward detector geometry, catching the particles that spray out in the direction of the beam. Bell Roman 2 uses a symmetric electron-positron collider, where the initial energy is precisely known, making the missing energy measurement cleaner. Both experiments have searched for these decays and placed stringent limits on the branching fraction, how often the decay occurs. So far, the measured rates are consistent with the standard model. That means any extra-dimensional effects must be very weak, or the particles that carry energy into the bulk must have masses beyond the reach of these experiments. The limits are complementary to those from direct LHC searches. At the LHC, missing energy signals come from high-energy collisions that produce gravitons or other invisible particles. Those searches probe the high-energy regime. The B-meson decays probe a much lower energy but a much higher precision, because the decays are so rare that even a tiny extra contribution becomes noticeable. Together, the two approaches cover a wide range of possible extra-dimensional scenarios. The fact that both are quiet tells physicists that extra dimensions, if they exist, must be hidden in a very specific way. But the search is not over. Bell Roman 2 is still collecting data, and its sensitivity will improve as it accumulates more collisions. LHCb is also undergoing upgrades that will allow it to detect even rarer decays. The null results so far are tightening the noose, but they also leave room for surprises. And right now, there is a different anomaly in the world of particle physics that has everyone's attention. It involves a particle called the muon, and the way it wobbles in a magnetic field does not quite match theoretical predictions. That discrepancy, known as the muon G-2 anomaly, could be a sign of new physics, including extra dimensions. A muon wobbles in a magnetic field slightly more than theory expects. That wobble, measured with extraordinary precision, reveals the particle's magnetic moment. The anomalous part of that moment, the small deviation from the simple Dirac prediction, has been measured to better than 1 part per billion. Yet there is a persistent gap between the measured value and what the standard model predicts. The discrepancy stands at about 4.2 sigma, meaning the chance it is a statistical fluke is less than 1 in 60,000. While not yet the 5 sigma certainty required for a formal discovery, this anomaly has drawn intense attention from physicists across the world. Many explanations have been proposed, including supersymmetry, new heavy particles, and extra dimensions. The extra-dimensional contribution would come from virtual Kaluza-Klein modes. These are the heavier partners of the photon and other standard model particles that can briefly pop into existence and then disappear. They would affect how the muon interacts with the magnetic field, shifting the magnetic moment by a small amount. The observed shift, if it holds, could match the predicted effect of a low-scale extra dimension or a warped scenario. The experiment that produced this measurement is the Muon G-2 experiment at Fermilab. It uses a powerful magnetic storage ring where muons are injected and circulate for many thousands of laps. As they travel, their spin precesses or wobbles relative to their direction of motion. The rate of that precession is measured by detecting the electrons produced when the muons decay. Over several years of data collection, the experiment has reached a precision of about 350 parts per trillion. The next round of analysis will include even more data, and the goal is to cut the uncertainty in half. On the theoretical side, the standard model prediction is also being refined. New calculations using lattice QCD and advanced perturbation theory are reducing the systematic errors. If the anomaly persists after these improvements, extra dimensions will remain a plausible cause. But the muon is not the only particle that might feel the influence of hidden space. The electron's magnetic moment has been measured to even higher precision and matches theory perfectly, which already places tight bounds on some extra-dimensional scenarios. The muon, being heavier than the electron, is more sensitive to new physics, which is why it shows a hint while the electron does not. The next step is to push the measurement further and to test the same idea using a completely different technique. That technique involves atom interferometry, where the quantum wave nature of atoms is used to measure forces with unmatched sensitivity. Atom interferometers split clouds of atoms into quantum superpositions. A laser pulse acts like a beam splitter, dividing the cloud into two paths. Each path follows a different trajectory through a vacuum chamber. Another laser pulse then recombines the two halves. Where they meet, they interfere, creating a pattern that depends on how much they were pulled by gravity along the way. That interference pattern is exquisitely sensitive, capable of measuring gravitational acceleration to a few parts per billion. In recent years, researchers have pushed this technique to its physical limit, using test masses separated by less than a millimeter. The goal is not just to measure gravity more precisely, but to test whether Newton's inverse square law holds at those tiny distances. In ordinary physics, the gravitational force between two-point masses falls off as 1 over the distance squared, but extra dimensions would modify that law. If a hidden dimension is large enough, gravity could leak into it, weakening the force at certain scales. Alternatively, a warped extra dimension could create a new short-range force, a so-called Yukawa force that adds a tiny pull or push on top of Newtonian gravity. That extra component would have a characteristic range, roughly the size of the extra dimension itself. Atom interferometers are ideal for detecting such a force because they measure the acceleration of a cloud of atoms relative to a nearby test mass. At Stanford University, researchers led by Mark Kasevich built an atom interferometer that dropped laser-cooled rubidium atoms past a dense tungsten mass. The tungsten mass was shaped like a dense cylinder only a few millimeters wide. As the atoms fell, the interferometer measured how much the tungsten pulled them sideways. The experiment placed the test mass and the atoms as close as 150 micrometers apart, just twice the width of a human hair. At those separations, if extra dimensions existed with a range larger than a few tens of micrometers, the deviation from Newtonian gravity would have appeared. No deviation was found, which means any extra dimensions must be smaller than about 30 micrometers. Meanwhile, a group at the University of California, Berkeley, led by Holger Muller, used a different approach. They dropped atoms from a height of about 1 meter inside a vacuum chamber and measured the gravitational acceleration with two separate interferometers stacked vertically. By comparing the two measurements, they cancelled many environmental errors and achieved an uncertainty of just 3 parts per billion. That precision allowed them to test the inverse square law at separations from a few millimeters down to about 1/10 of a millimeter. Again, no anomaly appeared. The null results from both experiments have significantly narrowed the allowed size of large extra dimensions, but atom interferometry is still in its early days. The next generation of experiments will use even colder atoms, perhaps cooled to just a few billionths of a degree above absolute zero. At those temperatures, the atomic wave packet becomes very large, spanning several micrometers, which actually helps the interferometer resolve forces at even shorter distances. Researchers are also developing chip-based atom interferometers, where the entire measurement happens on a micro-fabricated device. Those chips could place the test mass just a few micrometers from the atomic cloud, pushing the search to scales where extra dimensions would be much harder to hide. If a deviation is ever detected, it would be a direct sign of new forces, and extra dimensions are one of the most natural explanations. Beyond the laboratory, the same technology is being considered for space-based missions. In microgravity, atom interferometers can run for much longer times, dramatically increasing their sensitivity. The proposed MAGI's mission would place atom interferometers on satellites to search for gravitational waves and test gravity at astronomical scales. At those scales, extra dimensions could leave a different kind of imprint, a subtle shift in the way gravitational waves propagate across the cosmos. The interplay between laboratory experiments and cosmological observations is tightening the net around extra dimensions with every passing year. The oldest light in the universe holds clues to hidden dimensions. It is the cosmic microwave background, the faint glow left over from the Big Bang, a snapshot of what the universe looked like when it was just 380,000 years old. That light carries an imprint of everything that happened before, including the very first moments of inflation, when the universe expanded faster than light. And if extra dimensions existed during that inflationary era, they would have left subtle marks in the glow we see today. The Planck satellite spent years mapping the temperature of this light across the entire sky with extraordinary precision. One of its key measurements is the power spectrum, a graph that shows how much the temperature varies from one spot to another at different angular scales. The shape of that graph follows a very specific curve predicted by standard single-field inflation. Extra dimensions could modify that curve in several ways. They could change the tilt, making the spectrum slightly redder or bluer than expected, or they could introduce a gradual change in the tilt itself across different scales, a signature that the physics of inflation was not constant. Planck measured the spectrum with such accuracy that any running larger than about 1 part in 100 would have been detected. No such running was found, which already rules out many extra-dimensional models where inflation is driven by a scalar field living in a higher dimensional bulk. But the CMB offers more than just the power spectrum. It also carries information about non-Gaussianity, the degree to which the temperature fluctuations depart from a perfect bell-shaped distribution. In many inflationary theories, if extra dimensions are present, the interactions during inflation would produce a specific type of non-Gaussianity, often called local or equilateral. Planck looked for these patterns and found no statistically significant signal. The limits are now so tight that they exclude many Brane inflation scenarios and strongly constrain how extra dimensions could have shaped the early universe. Another critical measurement is the tensor-to-scalar ratio. This number compares the strength of gravitational waves produced during inflation, the tensor modes, to the density fluctuations that seed galaxies, the scalar modes. Extra dimensions can amplify the production of gravitational waves, especially in models where the inflattened field is close to a brane or where the extra-dimensional geometry is warped. A high tensor-to-scalar ratio would be a strong hint of such physics. Planck, combined with data from the Bicep and Keck experiments, has placed an upper limit on this ratio. It must be less than about 0.03. That is a very small number, and it means that if extra dimensions were present during inflation, they must have been configured in a way that suppressed gravitational wave production, or inflation itself must have happened at a much lower energy scale than some models predict. All these constraints are indirect. They do not prove extra dimensions exist or do not exist. Instead, they guide theorists toward the few remaining possibilities. For example, the absence of running and non-Gaussianity favors models where extra dimensions are small and static during inflation, not dynamically involved. The low tensor-to-scalar ratio points toward inflation driven by a flat potential, which is easier to achieve in some extra-dimensional setups than others. These cosmological tests are powerful because they reach back to the very beginning of time, probing energies far beyond what any collider can achieve. They tell us that if extra dimensions exist, the simplest versions are already ruled out. The surviving models must be more complex, perhaps with additional fields or specific symmetries. And that is where the next generation of experiments comes in. Future colliders, such as the proposed Future Circular Collider or the Compact Linear Collider, will push the search for extra dimensions to energies of tens of trillion electron volts. They will look for Kaluza-Klein particles, micro-black holes, and missing energy signatures with far greater sensitivity than the Large Hadron Collider. The CMB has narrowed the stage. The next act will be played out in the collisions of particles accelerated by human hands. The next generation of particle colliders will reach energies 10 times higher than anything built before. The Future Circular Collider, or FCC, is a proposed giant ring that would stretch for 100 kilometers underground near Geneva. It would smash protons together with a total energy of 100 trillion electron volts, roughly 7 times more than the Large Hadron Collider can achieve. At those extreme energies, the production of Kaluza-Klein gravitons and other extra-dimensional particles would become far more probable. Instead of hunting for a single faint signal buried in background noise, physicists would see a cascade of events, a whole tower of new particles appearing at predictable masses. That tower would be the unmistakable fingerprint of an extra dimension. Lepton colliders like the International Linear Collider, or ILC, and the Compact Linear Collider, known as CLIC, take a different approach. They smash electrons and positrons together, not protons. Electron-positron collisions are much cleaner because the initial state is precisely known. There are no messy remnants from proton fragments to obscure the signal. If a Kaluza-Klein graviton is produced, it would appear as a single narrow peak in the energy distribution of the outgoing particles, a clean bump that cannot be confused with background processes. These machines can also measure the spin of any new resonance, confirming whether it is a graviton or something else. The FCC is still in the planning phase, with construction possibly starting in the late 2040s. The ILC has a design ready and awaits funding decisions from international partners. CLIC, a linear collider that uses a novel two-beam acceleration technique, is also on the drawing board. Each of these machines extends the search for extra dimensions far beyond the reach of the Large Hadron Collider. If extra dimensions exist at the TV scale, these future colliders will almost certainly discover them. If they do not, the null results will push the fundamental scale to tens of trillion electron volts, making extra dimensions vanish beyond even the most ambitious human-built machine. But as the colliders grow more powerful, a different kind of experiment is being refined on a benchtop using neutrons. Neutrons are electrically neutral and can pass through matter without being deflected by electric fields. That makes them perfect probes of short-range gravitational forces. In the next generation of tabletop tests, ultra-cold neutrons are sent through narrow slits or bounced off mirrors, and their trajectories are measured with extraordinary precision. If extra dimensions exist at the micrometer scale, the neutrons would feel a tiny extra pull that bends their path. These experiments are small, quiet, and cheap compared to the collider giants, yet they probe the same fundamental question: is there more to spacetime than the 3 dimensions we see? Neutrons falling under gravity reveal their quantum nature in a remarkable experiment. In a laboratory in Grenoble, France, a group called qBounce sends ultra-cold neutrons through a vertical tower. These neutrons are cooled to a temperature just a few millionths of a degree above absolute zero, so they move at walking speed instead of thousands of meters per second. They are dropped from a height of a few centimeters onto a polished mirror below. As they fall, they bounce off that mirror, and each bounce is recorded. The neutrons behave not like tiny balls but like quantum waves, forming discrete energy levels similar to the orbitals of an electron in an atom. The lowest energy state sits just a few tens of micrometers above the mirror surface. By measuring how many neutrons occupy each level, physicists can determine the shape of the gravitational potential near that mirror. If extra dimensions existed at the micrometer scale, they would add a tiny extra force, a Yukawa-type attraction, that would shift the energies of those quantum states. The qBounce collaboration has measured these populations with extraordinary precision. They see no shift, no anomaly. The null result places a limit on any deviation from Newtonian gravity at a distance of a few micrometers. That limit is among the most stringent for large extra dimensions. effectively ruling out any hidden dimension larger than about 10 micrometers in size. The experiment is quiet, small, and takes years of painstaking work, yet it reaches into a regime where colliders cannot go. It probes gravity directly at the scale where extra dimensions would reveal themselves. And because the measurement is so clean, it stands as one of the strongest constraints on the simplest models of large extra dimensions. This tiny, patient measurement on a tabletop has closed a door that particle colliders cannot even open. But the universe itself offers another, far more extreme test. In the cores of exploding stars, matter is compressed to densities beyond anything on Earth, and the way those stars cool and release neutrinos could carry the faintest whisper of hidden dimensions. A star explodes and its ghostly particles carry a cosmic secret. When a massive star reaches the end of its life, its core collapses into a neutron star or a black hole. In that violent instant, a flood of neutrinos is released, carrying away 99% of the gravitational binding energy. In the first few seconds after collapse, a typical supernova emits more neutrinos than the Sun will produce in its entire 10 billion-year lifetime. These particles stream outward through the star's outer layers, barely interacting, and then race across the galaxy at nearly the speed of light. If a supernova happened in our own Milky Way, detectors on Earth would catch a sudden burst of these neutrinos, a signal lasting only 10 to 20 seconds. That signal carries a wealth of information about the physics inside the collapsing core, and if extra dimensions exist, that signal would be altered in a very specific way. The core collapse is so dense and hot that neutrinos can become trapped for a short time before diffusing out. In ordinary physics, they escape gradually, cooling the star and setting the duration of the burst. But if extra dimensions exist, some of that energy could be siphoned away into the bulk, the higher dimensional space beyond our brain. Those hidden channels would act like an extra cooling mechanism, draining energy that would otherwise remain in the neutrino population. The result would be a shorter burst because the star cools faster, and a lower total number of neutrinos reaching Earth because some of them never get created or get lost on the way. The shape of the neutrino signal, the time profile of how many arrive each second, would be compressed. Instead of a steady 10-second tail, the signal might fade in just a few seconds. Additionally, the average energy of the neutrinos could change. If energy leaks into the bulk, the neutrinos that do escape might carry less energy than expected, shifting the spectrum toward lower energies. All these signatures would be detectable by next-generation neutrino observatories. Hyper-Kamiok and a massive water Cherenkov detector under construction in Japan would catch tens of thousands of neutrinos from a galactic supernova. Its sensitivity is so high that it could distinguish a 10-second burst from a 5-second burst with great confidence. The Deep Underground Neutrino Experiment, or DUNE, uses liquid argon detectors and is especially sensitive to electron neutrinos, which play a key role in the early phases of core collapse. DUNE would see the initial neutronization burst, a spike of electron neutrinos that occurs in the first few milliseconds. If extra dimensions are present, that spike could be weaker or delayed because some of the energy leaks away before the burst can form. Comparing the two detectors, each measuring different flavors and different aspects of the signal, would provide a powerful cross-check. A joint observation would make it very hard for an extra-dimensional energy loss to remain hidden. But we have not seen a galactic supernova since the one in 1987, and that was in a nearby dwarf galaxy, not our own. When the next Milky Way supernova occurs, it could happen at any moment, and these detectors will be ready. Until that star lights up our detectors, we can only refine our predictions and wait for nature to reveal its secrets. The timing and shape of that neutrino burst could be the final clue, the one that confirms we live in a universe with more than 3 dimensions. And that brings the search full circle, from the smallest particles to the largest explosions, all pointing toward the same hidden structure of spacetime. A single supernova could one day confirm the existence of extra dimensions. That weight perfectly captures the state of the entire search. Across the spectrum of 20 very different experiments, from the thunderous collisions inside the Large Hadron Collider to the patient silence of a tabletop torsion balance, from the ancient glow of the cosmic microwave background to the ghostly neutrinos of a collapsing star, humanity has built an extraordinary net. Each experiment probes a different corner of possibility, a different length scale, a different energy regime. No single test can rule out extra dimensions entirely, but together they form a web so tight that any hidden dimension must be extremely small or extremely subtle to have escaped detection so far. The Large Hadron Collider has crashed protons together at the highest energies ever achieved and found no missing energy, no micro black holes, no graviton peaks. The torsion balances and atom interferometers have measured gravity down to a hairbreadth and found the inverse square law intact. The gravitational wave observatories have listened to the ringdowns of merging black holes and neutron stars and heard nothing out of the ordinary. The Planck satellite mapped the oldest light in the universe and saw no deviation from standard inflation. The neutrino detectors wait for a supernova that could come tomorrow or 1,000 years from now, ready to catch the whisper of energy leaking into a hidden bulk. This collective silence is not failure. It is a triumph of precision. Every null result has narrowed the allowed space, forcing theorists to refine their models. The simplest versions of large extra dimensions are already ruled out. Warped dimensions must be very small. Only a few specific configurations remain viable, and those are being cornered by the next generation of experiments. The search has transformed from a wild guess into a tightly constrained scientific question. What would a confirmed detection mean? It would be one of the most profound discoveries in the history of science. It would confirm that spacetime has more than 4 dimensions, that our universe is a slice of a larger reality. It would unite gravity with the other forces in a way that has eluded physicists for a century. It would rewrite cosmology, particle physics, and our very conception of what space is. It would open a new frontier, not just for research but for the imagination. The universe would become bigger, stranger, and more wondrous than we ever thought. If this journey fascinated you, please consider leaving a like and subscribing to the channel. Your support helps us continue exploring the deepest mysteries of the cosmos, and I would love to hear your thoughts. Which of these 20 experiments do you find most promising? Do you think the first evidence will come from a collider, a gravitational wave observatory, or something completely unexpected? Share your perspective in the comments below. Until next time, keep looking up and questioning the fabric of everything.